today's topic is something that's near and dear to my heart as we go through all of the just the day-to-day SIS engineering, project work, training class work. The definition of safety instrumented functions today runs into exactly the same problems that it always has ever since the inception of the functional safety standards, in that there's kind of a handoff between the risk analysis, hazard and risk analysis phase and the SIS engineering phase, and communication is lacking. I will just leave it as that. Many times when you're looking at a HAZOP, or specifically a HAZOP, maybe even a LOPA, they'll be, okay, well, we need to get 2 orders of magnitude credit from the temperature trip. The temperature trip. That's the only definition we have of the safety function, is the temperature trip. So kind of fleshing things out is the whole purpose of this webinar, and we're probably going to codify this into a full official training class in the Connexus Process Safety Training Center. So that's part of what we're doing here. So let me go ahead and get into it. I'm going to go ahead and share my screen and put up the presentation slides for today. Let me put us in full screen mode. There we go. So the topic of today is SIF definition. SIF definition is an absolutely critical task that needs to occur very early in the SIS safety lifecycle, specifically during the hazard and risk assessment phase. We need to clearly define what the safety instrumented function is, even as we're going through hazard and risk analysis. And then that definition is going to carry through SIL verification, safety requirement specification, all the way throughout the rest of the safety life cycle. Mistakes in SIF definition get carried all throughout the rest of the safety life cycle, and they can lead to a lot of problems, including the complete inability to achieve your required SIL targets, massive amounts of extra equipment, unnecessary increased testing requirements. And all of this stems from the fact that you didn't accurately tie what your hazard is to how you detect it and what actions you need to take as a result of that detection of an unsafe state. So first off, let's talk about the handoff between PHA and layer of protection analysis. For those of you that do them as separate activities, some of you, granted, are going to be doing basically a LOPA on every PHA, every HAZOP deviation. In that case, you're going to be doing this regardless of whether or not you think there's going to be a safety instrumented function there. Those of you that have talked to me before, have been in my training classes, know that I come at hazard and risk analysis from the perspective of an instrumentation and control engineer, as opposed to the perspective of a process safety management practitioner. So my objective when I'm going into the hazard and risk analysis is, there is a collection of equipment that I need to design. So I need to set performance targets for that equipment to allow me to perform that design. So I am very, very concerned about the definition of the safety instrumented function, whereas some PSM practitioners are just generally interested in achieving a tolerable level of risk for the plant as a whole. And the safety instrumented function is just one of the ways to get there. So there's not as much care and attention in the definition of the safety instrumented functions during that phase of the process. So when we're looking at scenarios that need to go through LOPA, there are a couple of triggers that are going to tell you that you need to go into a LOPA. So bullet point number 2, let me go ahead and bring up my laser pointer. Bullet item 2 is what most PSM practitioners focus on, and in a lot of cases, it's the only thing that they focus on, which is I'm doing my PHA. And when I'm doing that PHA, I come to a scenario that has a high level of risk or a high level of consequence. So when you see a consequence that's high or a risk that is high, that triggers the need to do a layer of protection analysis. And the thought process there is high consequence of events need more rigor in how we perform the risk analysis. So going through selected PHA scenarios is great, but unfortunately, based on past experience, we know that using that process is going to leave a lot of gaps, especially if you're an SIS engineer. You know that a lot of times you have safety instrumented functions that are shown on your P&IDs that don't show up in your hazard and risk analysis. You have no target for the basis of your design, and now you're kind of stuck. Which is why item number one in my mind, not as a PSM practitioner, but as an SIS engineer, is that if my piping and instrumentation diagrams are showing that I have a proposed by the licensor or the engineering company or existing safety instrumented function, I must do a LOPA regardless of what the PHA said, because I need to select a performance target. Even if that performance target is still 0, it's still necessary for me to have a basis of design for that equipment. And that basis of design is going to be based on the risk analysis. So what are your existing and proposed SIFs? Item 1, item 2, what are those high hazard scenarios from the PHA? But then you might also want to look at some other things in terms of, well, what are the interlocks that are recommended from other industry standards? So a great example would be NFPA 85 for boilers, gives you a list of safety instrumented functions that are required to be employed in the design. Similarly, API 556 would give you recommendations for what you should employ for fired heaters in process industry applications. So if there are industry standards for pieces of equipment like fired heaters or rotating equipment, look at their recommendations and make sure that you've either employed those functions or you've at least analyzed those functions to justify not implementing them. So the resources for determining what you need to go through the LOPA mill includes process hazards analysis reports. You're also going to be looking at cause and effect diagrams to see what safety functionality is employed in a process design and or in an existing plant. You're going to look through your P&IDs for things that look like safety instrumented functions. And that might seem odd if you're a PSM practitioner, but if you're an SIS engineer, you can look at a P&ID and immediately go, that's part of a SIF. Just by the instrumentation that's used and how it's represented. And then also you're going to want to look at those industry standards for equipment design to make sure that you have your appropriate set of safeguards. Now, once we get into that LOPA phase, if there is a safety instrumented function that is defined as part of the safeguard list, or you're simply, you note that it exists and you need to do a LOPA for it, we need to be careful about how we define that safety instrumented function, how we document it, and where that documentation eventually resides. So let's start out with a technical definition. Now, sorry about that. Now, I've already mentioned to you that this set of information was originally presented to an ISA safety conference in 2003. So the ISA safety conference in 2003, the standard of record was ISA 84 1996. This even predates the 2003 version of the IEC 61511 standard. So we're going back in time here. So if the definition that you're looking at doesn't match the definition that's in the new 2016 version of the standard, well, you have to understand where the vintage of these definitions going all the way back to 1996. So what is a safety instrumented function? It is a function that is intended to be implemented by the SIS, which is intended to achieve or maintain a safe state for a process with respect to a specific hazard. So I take that back. This was 2003, so it was the 2003 version of the 61511 standard that this definition came from. But it's still not the 2016 definition, which has gotten a little bit more complex. So if you want to get a deep dive into the definitions in the IEC 61511 standard, I have a functional safety podcast series. You could check Apple Podcasts or Spotify. Search for Connexus, and there's a series of podcasts where I went over all of the definitions in the 61511 standard. Currently, I'm in section 5, if you're kind of following along with my approximately weekly, and everyone who's, listen to the podcast knows that sometimes I get busy and skip a couple weeks. But I'm in section 5 now, which means I've gone through all the definitions, and from that kind of my definition and my opinion on how some of the definitions were written and what they look like. So as a result, you'll see I have this practical alternative to the definition. So the practical alternative is not in the standard, but it's maybe a little bit more appropriate and a little bit more informative than what is actually in the standard. So my practical alternative is specific actions to be taken under specific circumstances, which will automatically move the chemical process from a potentially unsafe state to a safe state. Okay, so when we're defining those safety instrumented functions, we need to know what the actions are, kind of on the right-hand side of the drawing, and we need to know the circumstances and how we detect those circumstances on the left-hand side. Right out of the gate, this is highlighting the weaknesses that many times you will see coming out of a PHA, where a safeguard will be, temperature measurement 101 is my safety instrument function. Well, you only told me what the sensor is. You didn't actually even tell me what the unsafe state that I'm trying to detect is. You definitely didn't tell me what action that I need to take. And both of those things are absolutely essential throughout all of the rest of the life cycle. So right here, this is the one that I am going to apologize for the absolute most, because when I converted my slides from the old format to the new format, the colors of things changed and now they're essentially invisible. But what I wanted to highlight with this slide is that a safety instrumented function is not just the logic solver. It's not just the measurement. It is everything from pipe to pipe. So when I'm defining my safety function and I'm doing my SIL verification calculations, I need to know everything about the function from pipe to pipe. That includes not just the transmitters, but interface devices between the transmitters and the I/O cards, process connections that may impact your ability to achieve the SIL, input cards, output cards, CPUs, processors, other associated electronics and logic solver system, interface devices between the output card and the actual final element itself, like solenoid valves. All of that is necessary to define, maybe not in the excruciating level of detail that you need to perform SIL verification calculations, but when you're in that first pass at the SRS, when you're defining the safety function, you need to define what I'm trying to detect and what actions I need to take when I detect that situation. The definition of the safety instrumented function is necessarily going to come out of the hazard and risk analysis, and it is what we are assigning a SIL target to. So when you're assigning a SIL target, you're not assigning it to the plant as a whole. You're not assigning it to the logic solver. You're not assigning it to a unit operation like a fired heater. There is a certain hazard that the safety instrumented function is intended to protect against. And the SIL target is assigned to the collection of equipment that is intended to mitigate the consequences or prevent the consequences of that specific hazard. So there's a one-to-one correlation between a hazard you're intended to protect against and the set of equipment that is going to do that that protection, that prevention. So not that anyone needs another tutorial on what the SIL levels are, but SIL levels are defined as order of magnitude probability of failure on demand. SIL 1 being the lowest, SIL 4 being the highest, where SIL 1 has a probability of failure between 10% and 1%, and then SIL 2, 1% to 0.1%, order of magnitude step changes for each SIL number. And then most of you are, like myself, are going to use risk reduction factor because we prefer whole integers to scientific notation. But the risk reduction factor is just 1 over the probability of failure on demand. So as we're doing this risk analysis, or as we're selecting the SIL target, we are doing it based on risk. And that was done very specifically, very deliberately for originally the ISA Standards Committee, and now it's moved out to a larger group of people in the IEC committee. And that's because we didn't want to prescribe what the design of a safety instrumented function looks like. Instead, what we wanted to do was allow you to have the flexibility you need to select that target yourself based on, basically, we're taking the risk, the likelihood that something is going to go wrong, and the consequences if it does go wrong. We're going to allow you to calculate that risk and then design your SIS so that it provides the appropriate amount of risk reduction. So we calculate the risk, compare that against what's tolerable, and make up the difference with our safety instrumented function. So the way that works, and some of you might recognize this from my SIS, my original OG LOPA book that was released back around 2000, the 2000 timeframe, where I look at the process of risk analysis in 2 dimensions, whereas if you look at the standard, it will try to look at it in 1 dimension only, frequency. But I look at it in the consequence dimension also. So when you're trying to decide what SIL you need, there's kind of an inherent level of risk up here. And that inherent level of risk is a function of the process design, the process operating conditions. What is the largest consequence that it can occur, and what frequency will occur with no protection? But then we're going to, in our risk analysis process, define risk reduction mechanisms like non-SIS likelihood reduction, which will drop you down the likelihood axis, but it won't change consequence. Things like relief valves, rupture discs, check valves will prevent the consequence from occurring, so they reduce the likelihood. But if the consequence does occur because those measures fail, it's the same as it would be if that safeguard didn't exist. So those allow you to travel down the likelihood scale, but they don't change the consequence. You can also do consequence reductions like containment dikes and emergency scrubber systems. Those things are going to decrease the consequence of the event if it happens, but they don't change the frequency at which it will happen. So a containment dike will minimize the size of your pool, but it doesn't prevent that pool or reduce the likelihood that that pool will be generated. Safety instrumented systems work on the likelihood domain. Safety instrumented systems don't make a consequence smaller, they make it less likely to happen. And with each SIL number that you apply, you are reducing the likelihood by 1 order of magnitude. So if I have a 1 in 10 event and I apply a SIL 1 safety function, I'm going to reduce the likelihood from 1 in 10 to 1 in 100. If I have SIL 2, 1 in 10 to 1 in 1,000. SIL 3, 1 in 10 to 1 in 10,000. Order of magnitude decreases in likelihood, but they do not change the consequence. If the SIS fails, you're going to get the same consequence as if you had no SIS at all. All right, so now let's drive down a little bit more into the SIF definition process. So I know I need to do a risk analysis to set a target for this collection of equipment, but kind of the key message today is, how do I define what that set of equipment is? What guidelines and rules do I use? And how do people get themselves into trouble when they're performing this task? So you might, if you look at an SIS, there's going to be a collection of inputs, there's going to be a collection of outputs, and there's going to be a logic solver. That is the SIS as a whole. But the SIS as a whole is going to have multiple different safety instrumented functions. So in this case, loop 1 might be this single sensor and this single output. Loop number 2 might be these 2 sensors and this 1 output. Loop number 4 might be this sensor, this output. Loop 5 would be 1 sensor and 2 outputs. So the SIS is going to get subdivided into a lot of different safety instrumented functions, but there's going to be sharing and commingling of sensors and final elements between those items. All right, David, I saw your hand up. How can I, what can I help you with?
Well, 2 questions. So on your previous slide, yeah, and this is kind of maybe a side topic question, but relief valves are typically listed as likelihood reduction as opposed to consequence reduction. And I've always thought of them as consequence reduction because their activation ultimately leads to an LOPC.
This is true. Absolutely. So it's all a matter of perspective, and more importantly, it's a matter of what does your vent and disposal system look like. So if you have a relief valve that's discharging to atmosphere, you basically moved where your consequence is located. So instead of your consequence being a rupture of your vessel and a major release, you're going to have a smaller release at a known location, but you can still have a consequence associated with it. So in that situation, your risk analysis got really complex because now you have 2 consequences that you need to keep track of, which pushes you into that kind of event tree analysis, focused QRA, quantitative bow tie, where in one scenario you have multiple consequences that you need to track. But in a lot of the major petrochemical installations, your relief valve opening is going to send you into a flare header where the safety consequence is essentially going to go to 0 because your vent and disposal system is going to allow you to safely handle that discharge. You're going to send it to a flare header. You're going to knock out the liquids. You're going to burn all the gases that are coming off. Now, that might still result in an environmental consequence that you want to track and make sure is tolerable. But most of the time, if you're only looking at safety and you're discharging into a flare header, you would consider that to be a preventive measure as opposed to a mitigative measure. But as you rightly mentioned, you need to think about, well, where is that material going? And is that another consequence that I'm going to need to keep track of?
Great, thanks.
Okay.
I don't know if you have time for another question.
No,
but it was
absolutely.
So on the next slide, you show that, for example, one sensor may be used by many different SIFs. So
Correct.
in that case, are those considered independent layers from each other, or can they, I mean, how does that go? Because, like, for example, in a BPCS, you can't do that. You know, you don't get to count that as independent layers, but in a SIS system, I guess you can, even though it's still relying on one sensor or one final element.
Okay, you're bringing up a very interesting and very complex topic that, you know, it occurs all the time in my day-to-day work. I know that I've discussed this with someone this week. Okay, so when you're looking at this kind of overlap, so this sensor right now is going to be used in 3 different loops. Is that okay? Is that not okay? Do I need to somehow mathematically account for the commonality of this sensor in these 3 different loops? Okay, first off, you need to go all the way back into your hazard and risk analysis and consider the scenario. So if loop number 4 here is used in a LOPA scenario, and specifically one cause to consequence chain. If loop number 4 is the only safety instrumented function in that cause to consequence chain, you're great. And if you have another cause to consequence chain that only uses loop 5, everything is good, because there's no commonality there, because the scenarios, when you look at the initiating event through the consequence, every initiating event through consequence is independent of every other initiating event through consequence, due to the, we'll call it the double jeopardy rule, because we don't expect that 2 initiating events, or it's really mathematically impossible for 2 initiating events to happen at exactly the same time. Now, there's a little bit of vagaries there in terms of common cause, but generally you're looking at a cause to consequence chain. You can have one safety instrumented function in there, and as long as the safety instrumented function doesn't have repeated equipment in that cause to consequence chain, you're okay. But if you have 2 safety instrumented functions in that cause to consequence chain, you cannot treat them separately. You're going to need to define a new safety instrumented function that contains all of that equipment and analyze it as though it's one SIF, even though you might not think about it that way when you're doing your documentation and your testing and such. That's going to come back a little bit later in the class, where I show you the concept of something called a staged safety instrumented function, where there are different sensors that are going to trigger different actions that are all related to the same hazard. And I'll show you how you have to necessarily treat that as one safety instrumented function. So hopefully that made sense, but if it's still a little bit fuzzy, we're going to hit it again because it's one of the guidelines I'm going to be talking about later.
Thank you.
All right. Okay, so kind of recapping this slide, there's a lot of sensors going into the logic solver, a lot of final elements coming out of the logic solver, and that entire collection is your SIS, but you're going to group together inputs and outputs individually based on a specific hazard. And that's kind of the primary thrust of what we're talking about and what the purpose of this webinar is. Okay, so if you look at a safety instrumented function, there are several things that even at the preliminary SRS during the hazard and risk analysis you need to define, and the members of the SIL selection or the LOPA team need to understand. And unfortunately, a lot of times it's only the first thing that gets talked about. Oh, yeah, we want to take credit for temperature switch 102. Okay, that only told me what to measure. That's not enough information for all the downstream engineering that's going to need to occur. In addition to that, I also need to know when you detect you've gone out of control, what do you do? What are your final elements? What are the actuation? The other thing I need to talk about is when do I do it? Maybe not to the degree of nailing down a set point in the LOPA, but the general process condition that we're trying to avoid is part of that when to do. And that when to do might actually be a complex sequence of logic. We need to spell that out even while we're doing the LOPA. And something that often gets neglected early in the process is how fast do we need to go from measure to react? What is the process safety time? What is the SIS response time? Now, that's something that doesn't get really critical until we're at the later stages of the life cycle and we're selecting the equipment. And part of that equipment selection is how fast does it operate? So you might need to put in things like pressure multipliers, fast-acting solenoids, using a solenoid instead of a positioner based on how much time you have to respond. But the set of people who can tell you how fast the item needs to respond are not included in the design process. So this how fast do I need to respond is something that's best done early in the safety life cycle, as opposed to trying to by hook or by crook get that information when you're actually selecting pieces of equipment. So this definition should be early on during the hazard and risk analysis phase. So an example would be I need to stop fuel gas flow in the event of a flame failure. I might need to supply emergency coolant to reduce temperature, open a blowdown valve to relieve excessive pressures, or issue a fire alarm and unlock fire water pumps. Okay, so when I am defining the SIF, here is a list of criteria that you need to think about, and this should end up in your SIF definition. And your SIF definition is primarily going to be included in your SIF list. So if you're a user of the Vertigo software, when you first click on the diamond icon, you're going to get the safety instrumented function list. And most of this information is going to be contained right there in that list. So number one, I need to know what is the hazard that I am trying to prevent. Often that's going to be documented in the definition or the description of the SIF. Item number two, what are the initiating events or causes of the hazard? And based on the initiating events and causes of the hazard, that's going to lead me to item three, which is how can I detect all of the initiating events? So what is the necessary and minimum set of sensors that will allow me to detect all of the initiating events? Next, I need to define, well, what is the logic? Also part of the description of the safety instrumented function. And then outputs. The outputs is hands down where I see the most mistakes in this process, because people kind of focus on the input side. A lot of times they don't define outputs at all, or the outputs get misdefined because they know from the cause and effect diagram that, well, when this input triggers, these outputs trigger. Well, some of those outputs may have nothing to do with preventing the hazard. So that's a big issue that we really need to address, and that's a problem that a lot of designers have in achieving their SIL targets because they over-specified what their outputs actually are. All we're looking for is minimum and sufficient set of actions to bring the process to a safe state with respect to the hazard that this safety instrumented function is intended to protect against. And finally, we're going to define what is the amount of time that's required to get to that safe state. So we're setting a maximum amount of time that SIF has to be able to get to its completion of the actions that it's taking. Okay, so let's start with some examples. And as we go through these examples, we're going to give you the guidelines, the numerical guidelines, tips that you need to follow when you're doing these definitions. Right here, I have a high pressure separator. This high pressure separator has a combination of basic process control on the left-hand side and safety on the right-hand side. As has been drummed into us since we first started looking at safety instrumented systems, these need to be physically and functionally separate. This is the set of equipment whose failure creates the hazard. It's the initiating event. This is the set of equipment that will detect, using LT102, detect that LIC01 has lost control and the separator level is going low, and then take the action of closing these two valves to prevent the level from continuing to drop, which could result in a runaway reaction. So when you look at the safety instrumented function definition, you'll see that number one, we're going to give a tag to the safety instrumented function. Back in 2003, I called it a SIF. I wasn't necessarily wrong. I was trying to make things easy for the participants, but if you are an aficionado of the ISA 5.1 standard, you know that the SIF would be safety indicating, I don't even know if there is an F as the last item. This doesn't meet the requirements of the ISA standard for how you define safety instrumented functions. So you could actually tag the safety instrumented function with an L because level is what causes this to happen. In the middle, you're going to use the letter Z or Z for those of you over in the UK. So Z implies, or actually defines, that it is a safety instrumented function. Now, I would have argued that there should have been an S in the middle because S is for safety, but S is so tightly, inextricably linked with relief valves that the ISA 5.1 committee said, no, let's just go ahead and use Z to convey that it's a safety instrumented function. And then the last letter is a C. It's a control because based on a measurement, an action is taken. That's the definition of a control. So in the ISA terminology, this should be an LZC. Or the thing that is more commonly done is you will use UZC instead of LZC because the letter U means multivariable. And for most safety instrumented functions, there are many variables that will trigger the action and many variables that are final elements. In going forward, you will see us and everyone, hopefully, when we're tagging safety instrumented functions, we will call it a UZC instead of a SIF or an I for interlock or whatever else. Next thing we're going to do is we're going to give it a description. So descriptions, we at Connexus have a very formal way now that we define safety instrumented functions that's a little bit different from what you see here. But ultimately, we're going to want to, number one, say, well, what is the piece of equipment that we're concerned with? That is the high pressure separator. What is the measurement that you're taking to determine that you've gone out of control? Low liquid level. And what is the hazard? Well, low level indicates a potential for downstream equipment overpressure. That's the hazard. And then what action are you taking? Closes liquid outlet valve. So a description in English that does all of that hazard definition is what you see here. So currently we're doing a little bit more. We're putting tag numbers in for pieces of equipment because this is something that you probably know is that if you say the high pressure separator, a lot of times operators are going to give you a blank stare because they know the high pressure separator is V105. So we'll put in high pressure separator for the engineers that don't know the tags. We'll put in the tags for the operators who don't know the official name of the piece of equipment. And that way everyone will better understand what's going on. So tag number, description. Then we're going to list out the inputs and possibly a voting indication if that's not intuitive or clear. And we might even also want to put in something like low level in the input to further describe what it is. So I've got level transmitter 2. It's 1 out of 2 voting. Then we're going to list out the outputs. So tag number of the piece of equipment. What is it supposed to do? So I've got a UV01 and I need that valve to close. And if you look at that tagging again, U is multivariable because there are many variables beyond just the level that will cause this valve to close. To be more precise, we probably should have called this a UZV because it's part of the safety instrumented system. The same way we probably should have called this an LZT because it's part of the safety instrumented system. The SIL target coming out of the LOPA is part of the SIF definition. And then the notes is a great place to put a lot of other information like the process safety time or minimum activation time. At this point in time in our Vertigo tool, we have a different location where you would want to specify this that shows up in the SRS but doesn't show up in the SIF list. But you know, with a relational database tool like Vertigo, it's easy to show stuff where you need it, but it's always available and not show it when you don't necessarily need it. Okay, I'm not going to talk much about process safety time. This slide, as you can see, did not cross over very well. I'll just suffice it to say it's a complex analysis that needs to consider where you're normally operating, what your trip point is, what the dangerous condition is, how much time elapses or how quickly the process can move. All those things need to factor in when you're calculating the process safety time. Okay, let's get into guideline number 1. So when you are defining your safety instrumented functions, the first guideline, the first thing you need to think about is what is the specific and identifiable hazard that the safety instrumented function needs to protect against. So in our first example, we're measuring level. And yeah, the SIF is there to protect against low level. But why? What does low level mean? That's important actually when you're doing your SIS design, because maybe low level is not the best way to detect the hazard that you're actually trying to protect against. And in a lot of cases, one measurement might actually protect against multiple different hazards with different actions and different safety instrumented safety integrity levels assigned to those different hazards. So don't stop at just what parameter did I measure. You need to think about what is the hazard really that measurement is trying to tell me is going to happen. And that's going to help me better define what the actions are and what my safety instrumented function actually looks like. So sometimes multiple hazards are going to use common pieces of equipment such as a single sensor. And if there are multiple hazards based on a single sensor, you need to separate it into different safety instrumented functions. So right now, as an example of that guideline, I'm going to show you something that everyone who is in oil refining or oil upgrading has seen, because this is the anti-backflow interlock that you're going to see on every hydrotreater or every heavy oil hydrotreater and every hydrocracker. You have a low pressure feed tank, maybe 50 to 100 PSI, and you're going to have an insanely powerful pump that's going to pressure up the liquid up to the reactor system pressure, which could be 500, 800, 1,000, and maybe even all the way up to 3,500 PSI in the case of a residual oil hydrotreater. Now, if this pump fails, I've got maybe 2,000 PSI of reactor system that wants to backflow into 100 PSI worth of feed tank, and that's basically either going to cause this feed tank to violently explode. It's just going to shatter. Or if you break your piping first, you're going to turn your feed tank into a rocket and launch it 300, 400, 500 yards away from where it started, which actually I know of a refinery on the West Coast where that actually happened. Okay, so that's one of the hazards that's intended to be protected against here. But why am I measuring this level? The level isn't going to tell me that the pump failed, but well, I kind of also need to protect this pump, because if I lose my forward flow, I'm going to over temperature this pump. I'm going to destroy its seals. I'm going to get a leak of hydrocarbon, which could catch fire, and I could have a large pool fire. Well, a large pool fire, because you blew your seals on the pump, is a completely different hazard from overpressuring and launching this feed tank, even though the same flow measurement is going to tell you that both hazards are about to happen. So let's look at that from how you would define the safety instrumented function, just looking at flow, or in this case, we're going to kind of separate them, because really the level is the best way to tell I'm going to have a dry suction on that pump, as opposed to low flow on the discharge telling me that I lost suction on that pump. So, and as I look at this, my goodness, this was 2003, and I've got, well, let me go over the descriptions, because I actually have my outputs mixed up. So this shutoff valve should be associated with the flow transmitter, and the level transmitter should be associated with the pump stop. So in your mind, in your mental notes, go ahead and switch the pressure, or switch the pump and the valve. So, all right. Now that we've mentally switched them, let's go and look at these two safety functions. So the first hazard I talked about is that backflow. So if I have low flow, what that means is I have a potential backflow hazard. So if I have a potential backflow hazard, I need to stop, I need to close this valve to prevent my reactor system from backflowing through my now stopped pump into my feed tank. I've got these double check valves, which is one of my IPLs, but that one IPL is not enough for the level of risk that we're talking about. So in a lot of cases, you're going to see this SIL assigned a SIL2 target. It's very common that the safety function gets assigned a SIL2 target for closing the valve. But if I close the valve, I'm also going to want to stop the feed pump. Why do I want to stop the feed pump? Well, I need to stop the feed pump because when I close the outlet valve, I'm going to now also deadhead the pump. And if I deadhead the pump, that's going to cause my secondary hazard, which is seal failure, loss of containment, and seal fire. So the hazard that we're protecting against with SIF 11 is the backflow hazard, but we're also going to stop the pump as a result of the low flow, but that's going to be a secondary safety function. I'm going to come back to secondary safety functions because that's going to be another one of the guidelines defining when you need a secondary safety function and what it is. So for this first safety instrumented function, the primary action is to close the shutoff valve. The secondary action is to stop the P11 pump. And when you have a secondary action, you're probably going to put that secondary action in the notes as opposed to in the description of the safety instrumented function itself. Now, I do also in this case have a secondary or a second safety instrumented function, which is intended to protect against the deadheading, or I'm sorry, the dry suction, cavitation, seal failure of this pump because you lost suction. And that's what the second safety instrumented function is. And it's loss of supply to the feed drum, which you can detect with LT11, and that's going to indicate the potential for a dry pump. And when that happens, you're actually going to take the same action. So when we look at this on a cause and effect diagram, FT11 is going to cause the pump to stop and the valve to close. LT11 is going to stop the pump and cause the valve to close. But for SIF 11, the primary hazard is backflow and the primary action is closing the valve. For SIF 12, the primary hazard is damaging the pump and destroying the seals, and the primary action is to stop P11. So that's why they must get separated into separate safety instrumented functions. And what you see on this page is what you will generally see when you do your risk analysis, that closing the valve to prevent backflow is typically going to be a SIL 2, whereas protecting against seal failure is typically a SIL 1 because the consequence is a lot smaller, and you're generally also going to have conditional modifiers that will reduce risk beyond what you're seeing in the first safety instrumented function. Okay, so that's guideline number 1. You need to look at what is the specific hazard, and for every specific hazard, define specifically how can I detect it and what is the action that is related to that hazard, and ignore all other actions. For guideline number 2, when we consider specific hazard, we may need to define multiple safety instrumented functions for a single hazard because there are initiating events that don't all share the same means of detection. Typically, we're going to separate our safety instrumented functions by initiating event that are detected by different instrumentation. A corollary to the guideline is that all of the instrumentation that can detect the progression from the incident through the hazard should be included in the SIF. So you don't define different scenarios for each SIF unless there are different causes that can be detected by different SIF. Okay, this is probably clear as mud to you right now, but let me give you the archetype, which is our fired heater. So for our fired heater, there are a lot of different sensors that can detect that you've lost flame and potentially are going to have a vapor cloud explosion if your unburned fuel gas cloud finds a source of ignition. You might have a high pressure switch that is indicative of you're going to blow your flame out because the pressure is too high, create a gas cloud, find a source of ignition, you're going to have a firebox explosion. If the pressure goes too low, you could lose your flame because it becomes unstable, create a gas cloud, find a source of ignition, firebox explosion. For your flame scanner, you can detect things like a slug of nitrogen or carbon dioxide that causes you to lose your flame, even though the pressures didn't change. And then that gas cloud will develop, find a source of ignition, and cause an explosion. So I've got 3 different measurements that are going to ultimately, in the big picture, detect loss of flame and prevent the firebox explosion. So one would think that I'm going to combine all these things together into one giant safety instrumented function, but you can't do that, because if you do that, none of these by itself can detect all of the causes, and you're basically going to be stuck saying, well, my safety instrumented function actually can't detect all of my initiating events, so it won't work. So what you need to do is you need to kind of unhook the hazard a little bit and look at the causes to determine, well, what interlocks, what SIS functionality is going to be able to detect this cause, and make sure to define it as that cause to consequence scenario. What equipment from my safety instrumented system sits in this cause to consequence scenario? I need to define that as a safety instrumented function. So what you will typically see, instead of one safety instrumented function where you're going to say, well, I've got a 3 out of 3 vote of PSL, PSH, and BSL, you're going to define it as 3 separate safety instrumented functions. So I'm going to define a low fuel gas pressure trip, which is low fuel gas pressure indicating a potential flame out causes a heater shutdown. Your second safety function is going to be high pressure. So high fuel gas pressure indicating potential flame out initiates a shutdown of the fuel gas. And then I've got flame out due to fuel gas contamination, which I can only detect with the flame scanner. So now that you've kind of set it up as a cause consequence rung, now you can better define, well, what is the part of that burner management system that can detect this cause and prevent the consequence? So for the hazard of low fuel gas pressure, you're actually going to have 2 measurements. You're going to know that your fuel gas pressure went low because you measured the low pressure. But if the fuel gas pressure went low, I'm not going to have a consequence until my flame is actually extinguished. So that hazard, before the consequence occurs, will also be detected by your flame scanner. So in this case, both my pressure switch and my flame scanner can detect that my hazardous condition is present. Either one of them independently can detect this situation. So my flame scanner and my pressure switch actually form a 1 out of 2 vote. Oh, well, that's quite interesting. A lot of people ignore this, and they will just try to achieve their SIL2 target, if that's what was picked, using just the pressure switch. But in reality, if you have a pressure switch and a flame scanner, you can include both of them, because both of these measurements are capable of detecting that the hazardous condition is present. Now, when I go down to the high fuel gas pressure trip, here's where I'm going to say the same thing, but I'm going to ask you to be cautious. So most people would not include the flame scanner in this hazard, because when your fuel gas pressure is high, you will detect that with a high pressure measurement. And if you blow your flame off because the pressure is that high, you will also detect that with the flame scanner. But there is a middle ground that's going to result in what's called a loaded or a bogged firebox, where you're putting in more fuel than you can burn, but not so much that the flame goes out, and now you've got a flammable atmosphere with hydrocarbons, carbon monoxide loading up your firebox. And if you give that, in that situation, if you give it air instead of cutting back fuel, you will cause the firebox explosion that you're intending to protect against. So right there, depending on how you actually define the hazard, you might not want to include this flame scanner. If you've defined your hazard as flame out, then yes, you can. But if your hazard is actually an overloaded, bogged firebox, then you cannot include that measurement. So hopefully you're kind of catching the overarching message here, which is, what is the actual hazard that I'm trying to detect, and what are the sensors in my logic solver, all of them, that are capable of detecting that hazard is present. So now in the case of contamination of the fuel gas, my pressure didn't change, so neither of my pressure measurements are going to be able to tell me that the hazard is present. The only thing that can tell me I've contaminated my fuel gas and put the flame out is the flame scanner. Okay, so those are basically what are all of the ways that can actually detect that the hazard is present. They are your inputs. Now, on your outputs, we're going to flesh this out a little bit more in the next guideline, but what is the necessary and sufficient actions to get to a safe state? So in order to get to a safe state with respect to this system, all I need to do is, if I close one out of these two fuel gas valves, I am going to stop putting fuel gas into the firebox, and I'm going to prevent an explosion. But you'll see that we also have another valve here. We have the double block and bleed. Why didn't I include the vent valve as part of my safety instrumented function definition? And the answer is because the vent valve doesn't do anything to prevent fuel gas from getting into the firebox in the immediate failure mode. So this vent valve is not there to prevent the primary hazard. Why is the vent valve there? Well, if I close my two fuel gas valves, my double block valve, and I am down for a long period of time, if both of these valves are leaking a little bit, eventually I'm going to leak through my closed shutoff valves, go into the firebox, accumulate gas in the firebox, and if I don't purge the firebox, when I light it off, I'm going to cause an explosion during light off. Well, that is a separate and distinct other hazard from the two scenarios, or the three scenarios that we talked about, which are during operation, you can cause a flammable gas cloud and explosion. As a result, opening of the bleed valve is not part of the core safety instrumented function. It's a separate auxiliary action that doesn't help you to achieve the safe state with respect to the primary hazard, but it is something that we want the safety instrumented system to do for other reasons. So that's your first introduction to auxiliary hazards. We're going to get into auxiliary hazards again a little bit later to kind of flesh it out a little bit more. Okay, guideline number 3. You're always going to want to differentiate between primary and auxiliary hazards. Oh, we just already talked about this, so let's flesh it out a little bit more. So even fully automated actions of a safety instrumented function, like opening a bleed valve in a double block and bleed, are only included in the SIF when they perform the primary or core function that's required to move the process to a safe state. So if you're putting fuel gas into the firebox and you lose your flame, you need to stop putting fuel into the firebox. Closing one out of the two shutoff valves will do that. Opening your bleed valve does not do that. It doesn't help you to do that. It doesn't contribute to that. It's there for an entirely separate reason, to prevent leaking that's going to be an issue during startup. So the opening of the bleed valve is not primary. It's not core to the safety instrumented function. Do not include it in the definition of your SIF. So if I look at a different example of an auxiliary reaction, let's look at a batch chemical reactor. So in this batch chemical reaction system, I'm going to be feeding material into a reactor, and over time, it's going to generate heat because it's an exothermic reaction. And I'm also supplying cooling water to the jacket of the reactor. But if I, for some reason, get an upset in my cooling water system, the temperature might start to go high, indicating that there is a runaway reaction. So in order to get to a safe state, so my core action is, if the temperature is high, stop feeding my reactor. If I stop feeding my reactor, the material will react, your reactant concentration will decrease, your reaction rate will decrease, the temperature will decrease. So in order to prevent the runaway reaction from occurring, all I need to do is close one out of these two valves. But you'll notice that the safety instrumented function is also going to drop out the solenoid valve that closes the level control valve. So downstream of the reactor, I'm dumping material out of the reactor into a separator, and there's a level controller that's going to allow liquid to go out to storage, and the vapor is going to go overhead to some other process. So when I trigger the safety function, I'm also going to close this valve. All right, let's go to the SIF list and see what we did about this. Well, we define the safety instrumented function as we normally do. So we give it a tag number, a UZC is what we should be using. We said, what is the measurement that we're making? What is the hazard that we're trying to protect against? And what action are we taking? So high reactor temperature that indicates that there's a runaway reaction is going to isolate the feed. Only isolate the feed. So how do we detect that there's a runaway reaction? We've got temperature transmitters 31 and 32 in a 1 out of 2 vote. That's our minimum and sufficient detection of a runaway reaction. Our outputs are to close the valves in a 1 out of 2 voting arrangement, and we've decided that we need SIL 2 for this. You'll also notice that we have LCV 31 close is one of the responses to that. It is the action, it's an auxiliary action. So when we say it's an auxiliary action, what we're saying is we're going to do this, but it's not part of the safety function. You don't need to close LCV 31 to prevent the runaway reaction. So why are we doing this? Well, in this particular case, if you're going to stop the reaction, we don't want the level controller, we don't want the level to continue to drain out of the system into the storage tank, because ultimately you're going to be sending vapor out to the storage tank. You might cause an environmental exceedance. And at the end of the day, when we restart the reactor, we simply want a level to be in here. So it's going to ease our startup. It's going to put us into a known state, but closure of this valve, and probably you're going to set this controller to 0% and manual. We're making life easy for the operator. We're taking work out of the operator's hands, setting the process into a known state so that it's easy to restart. But this action is not safety critical. It's not required to prevent the runaway reaction, so don't include it in your safety function. If you do include it in your safety function, you'll have XV, LV in a 1 out of 2 vote. In an OR gate with your level control valve in a 1 out of 1 vote, there's no way that that set of equipment is going to achieve SIL 2. So you're going to end up doing something silly like putting an extra dedicated shutoff valve on your level system when there's really no hazard that it's intended to protect against. So on that output side, absolutely critical to say, okay, based on this measurement, what is my hazard? And then for that hazard, what is the minimum and sufficient actions to get to a safe state? Those are the only outputs that you're going to put into your system, even if you have other actions. So you might look at that cause and effect diagram, and TT3132 is going to close these XVs, it's going to close the LV, it might do 10 other actions. Well, look at every action and ask yourself, does this action prevent runaway reaction? If it does not, do not include it in your safety instrumented function. All right, guideline number 4. A single SIF can contain several actions taken at different times, all intended to prevent the same hazard caused by the same initiating event. So this is kind of a concept that we talked about earlier. This is also going to be a stacked safety instrumented function or a staged safety instrumented function, where there are multiple final elements that are associated with a hazard, but you're going to try one first, and if that one doesn't work, you're going to do the second one or you're going to do the third one. So you're not going to activate the outputs all at the same time. You're going to stagger them and only activate the secondary and tertiary ones if the primary, or if the first one fails. And the reason that you would do that is the smaller the set of actions that you take, the less negative impact on the process and your ability to restart the process. So going back to this reactor system. So now I've added a little bit more equipment to this safety instrumented function. So I've got my reactor that's capable of suffering a runaway reaction. But in this case, I normally don't have cooling water applied. I've got a jacket to the reactor, but instead of triggering the cooling or having the cooling water running all the time, I'm only going to trigger it when a runaway reaction is starting to occur. So the initiating event might be that I lost my flow control and I'm overfeeding the reactor, or the initiating event might be that I overcharged the reactor with the first reactant and it starts to overheat more quickly. So in this case, my initiating event, let's just say my initiating event is upstream flow control failure. My safety instrumented function says, if the temperature goes high, I'm going to open the emergency cooling valve and I'm going to close the emergency isolation valves that are going to stop feed. But in this case, it's staged, so I'm going to do the cooling water first. And so I'll have a lower set point on temperature that's going to activate the emergency cooling water. Then I'm going to have a higher set point that says, if activating the cooling water didn't stop the runaway reaction, now I'm going to want to kill it, and I'm going to want to close the feed inlet valves. So what does that look like? Some people might say, okay, I'm going to take these temperature transmitters and opening the flow control valve the emergency cooling water valve. That's one safety function that I'm going to assign a SIL target to. And then I've got the same temperature transmitters at the high set point are going to close the inlet valves. And you would define that as two separate safety instrumented functions. Well, number one, it's not a good practice to define this as two safety instrumented functions. And actually, you can't. You're not allowed to define it as two safety instrumented functions, because there is a clause in the 61511 standard in clause 9 on allocation that says if you have you cannot have multiple safety instrumented functions on one sequence of events to cause to consequence. Because at the end of the day, you're going to be sharing your SIS logic solver at an absolute minimum. In this case, you're sharing your inputs. And if you treat them as separate safety instrumented functions, you can under-design, in this case, you can under-design your inputs, you can under-design your logic solver and still achieve tolerable risk, because you didn't acknowledge that, well, these two different functions are going to be using the same measurement device against the same cause-consequence pair. So what you actually have to do is treat the whole situation as one safety instrumented function. In your mind, you have to assume that the temperature went from normal all the way past the high trip point all at one shot, and all of your final elements activated. And the reason that you have to do that is because they are protecting against the same cause, they are protecting against the same hazard, and at a minimum, they're going to share the same logic solver. In this case, they actually also share the same inputs. As a result of that sharing, you cannot treat them separately. So instead of defining separate safety instrumented functions, you say that all of those output actions are in the safety instrumented function. So I will not have a runaway reaction unless XV31 fails and XV32 fails and FCV31 fails. The cooling water valve would have to fail, and both of the valves in the 1 out of 2 boat have to fail in order for my consequence to occur. So that's a stacked or a staged safety instrumented function. You don't treat them separately. When you run your SIL verification calcs, you run them at the same time, even though logically the output actions are going to happen at different set points and different actual points in time. All right, guideline number 5, I believe, is our last guideline. Occasionally, a shutdown is going to be made to prevent a primary hazard. But when you take that primary action, you created a whole brand new separate hazard that you need to protect against. So there's a concept of a secondary safety function, which is probably one of the most complex things to wrap your mind around, because your secondary safety instrumented function is going to have an output, but it's not going to have inputs, because the input is basically the logic. If the logic says to do this, then I also need to do that in order to prevent that secondary action from occurring. Okay, what does this look like? Let me give you the example of a chlorination reactor. And my chlorination reactor, I am going to have a liquid material in here. Let's say I'm going to charge my reactor with a hydrocarbon of some sort, maybe an olefin of some sort. And then I'm going to sparge chlorine into the reactor. And my chlorine molecules are going to bust those double bonds and attach themselves to my olefin to create a chlorinated hydrocarbon product. Now, if under the normal state of events, my chlorine is going to get consumed in the reaction, and there's going to be a negligible amount of chlorine that goes into the overspace and goes downstream. But if chlorine does go downstream, I am going to have a hazardous situation. So I've got a safety instrumented function that says if my concentration of chlorine in the overhead goes high, I'm going to want to stop sending chlorine into the reactor. So I'm going to have a double block 1 out of 2 vote preventing chlorine from going into the reactor. But I also have this extra little nibble here. And this extra little bit says, if I activate my safety instrumented function, I also want to open an inert gas valve. So the inert gas valve most of the time is going to be nitrogen. So I'm going to basically pressure up the cavity in between these two block valves with nitrogen to prevent anything from inside my chlorination reactor from backflowing into my chlorine system. Now, in the big picture, what I'm arguing to you is that the primary action is closure of these two shutoff valves is going to prevent the consequence of chlorine breakthrough. Opening of this inert gas valve to pressure up the cavity between these two valves is not going to do anything to prevent my chlorine breakthrough. This double block and pressure is at a minimum an auxiliary action. But what separates an auxiliary action from a secondary safety function is if the auxiliary action fails to occur, I'm going to get a new consequence, and that new consequence is separate and different from the consequence that the primary function is intended to protect against. So when we look at this, I've got a primary safety function that says if I get a high chlorine concentration in the overhead reactor, I need to shut down the reactor. So if my AIT 41 shows me high concentration of chlorine in the exhaust gas, close the two inlet valves. And the consequence of that might be small. It might be an environmental exceedance because I'm releasing trace chlorine gas to atmosphere at a high elevation, so it's not a safety consequence. But now I also have a secondary safety function. What is that secondary safety function? The secondary safety function says, if I have a reactor shutdown, then I need to put inert gas and pressurize the cavity between those two valves. Because if I backflow chlorine or backflow the hydrocarbon from my reactor into my chlorine system, I can have the reaction that was supposed to occur in my reactor occurring in my chlorine system, which could cause the chlorine system to over temperature, melt the piping, and cause a release of material, a loss of containment of chlorine. And that loss of containment of chlorine because of the backflow could have a much higher consequence than the function I was trying to prevent with the primary. In this case, we defined it as SIL2. But what's key to note is that closure of the double block and bleed prevents the chlorine in the off gas. That's one hazard. The UV43, the pressure valve, prevents backflow, which if you preventing the backflow is going to have an entirely separate dedicated consequence set, separate risk analysis. So you need to define those two safety instrumented functions separately from each other. And that comes to the end of the presentation. So Dave, I know you've got a question, but I'm going to basically also tell everyone that that's the end of safety instrumented function definition. I went through the 5 guidelines and I went through basically 5 cases of things that people actually might do wrong when they're defining their safety instrumented functions. So now that we're done with the core part of the presentation, I'm going to open the floor to questions.
So a question on this specific one that you mentioned here. So if your scenario was backflow, at what point do you decide that it's better to try to measure or quantify that backflow with a different instrument, like, for example, I don't know, a pressure transmitter or flow or something else, as opposed to just basing it on the reactor shutdown?
There are a couple of factors to that, and it's going to go back to the LOPA to say, is there and honestly, there is a differential pressure across this reactor that's going to trigger this shutdown too. just kind of letting you know that. And the reason in this case that there was a differential pressure shutdown that triggers the shutoff is that there are other causes of backflow beyond just the fact that my safety system shut off my chlorine flow. So you need to do your risk analysis, and what the reality of this analysis showed is that there are other situations, specifically if you shut down your vaporizer, that's also going to trigger a reverse flow in this situation. And that is its own safety instrumented function that is going to be detected by a high differential, or a low differential pressure there. So yeah, you got to go cause by cause through the risk analysis process. And in many cases, you will see that the secondary safety function by itself is not enough. I think Charlie had a question.
Yes, Ed, could you repeat, I believe I missed it, but could you repeat the difference between this being an auxiliary action being treated based on logic versus the example on the fired heater,
Yes,
in which we had to vent, but it did not apply to the logic. It was not connected to anything,
okay.
Right?
Absolutely. So here we have basically a double block and isolate. So in this case, we're going to pressure to isolate. In the case of the fired heater, we're going to bleed to isolate, to provide that positive isolation to prevent the backflow. So for this scenario, if you don't isolate and you get leak through, you're going to get a runaway reaction in the chlorine system. That runaway reaction is going to cause loss of containment and release of chlorine to atmosphere, which has a very high consequence severity. So basically, if this action didn't happen, you will get a high severity consequence that you need to mitigate. If I go back to my fired heater, if you don't get your positive isolation, you are going to get a slow trickle of gas over time into this firebox, which might accumulate to the point where you can generate a flammable mixture, which would cause an explosion. But the reason that we call this an auxiliary action instead of a secondary safety function is a matter of what is the risk and what is your basis of safety. So for the double block and bleed, the basis of safety against leakage and accumulation of gas in the firebox is not this vent valve. The basis of safety against that accumulation hazard is your purge function. So how are you really going to prevent that explosion at startup because gas leaked through? Well, before I put a light in my firebox, I'm going to go through a purge sequence to clear out anything that was in here and make sure that it wafts out the stack. I might send someone out with a portable gas detector to sniff the fired heater before you put the fire in the firebox. So there is a different mechanism that is intended to protect against that action in the fired heater case. In the case of this separator, I mean, if this level valve doesn't close, there is really no consequence. You just emptied out your separator. It's a pain in the butt for the operator because before they can run the process, they're going to need to backflow material out of storage into the separator so that they have a liquid level. But if you emptied it out, there's no consequence in reality. It's just a pain in the butt for the operator because it's a lot more work when they're trying to restart the plant. So it's all a matter of, if the action doesn't happen, what is the consequence? if the consequence is significant, if it's a significant safety consequence, you also need to look at, well, what is your basis of safety? Is this action taken by the SIF the only thing that I've got? Or are there other functions like the purge that are going to get me to a safe state? And they're going to get me to a safe state better, to where I will ignore it and call it an additional action. And then there are some additional actions that are literally so benign that there is no consequence. You're just literally trying to save the operator time during the startup process. Does that clarify?
Yes, perfect. Thank you.
Excellent. All right, Chris, were there any questions in the chat that I missed, or any hands up that I didn't catch while I was talking?
There's one in the chat here. It says in example number 2 for the fire heater, why the rotation of shutdown valves is 1 out of 2 and not 2 out of 2.
Ah, very easy. Okay, well, maybe easy, and I have to be careful of the knowledge and background of everyone that I'm talking to. In the IEC 61511, 61508 world, in all of the ISA training classes on functional safety, you're going to run into voting arrangements that we're going to call M out of N. So 1 out of 2, 2 out of 2. So for 1 out of 2, M is 1, N is 2. So N, the last number, is how many devices in total are there in the system. So in a 1 out of 2 system, there are 2 valves. I got valve number 1, valve number 2. The M is how many devices need to take an action to get to a safe state. So how many are required to vote to trip in order for the trip to happen? And in this case, we said it was 1 out of 2. It's 1 out of 2 because both of these valves are in series. And if I'm trying to stop flow and I have valves in series, if either one of those 2 valves closes, I'm going to get to a safe state. So if valve 21 closes, but 22 does not, 21 closing by itself gets you to a safe state. If 22 closes, but 21 does not, 22 by itself gets you to a safe state. So only 1 out of these 2 valves has to close to get to a safe state. So that's how it's been defined by IEC and ISA in the standards and the training classes. If you haven't used the ISA and IEC rules and techniques, or if you're new to it, you might think that I have 2, either one of them will get me to a safe state, so it's a 2 out of 2. No. While it might appear arbitrary, and maybe it is arbitrary, what has been decided by the functional safety community is N is the total number of devices, and M is how many must activate to get to a safe state. And in this case, if either one out of these 2 valves closes, you will get to a safe state. Thanks, everyone.